Hello YouTube, this is Carlos with CHS Electronics, and today I'm going to talk about my programmable DC load. Well, at least the third, actually it's the fourth rendition of the board that I have here. But this is the board. I have a unit that's been put together and tested and coded and all that good stuff, and it seems to work okay, although the ADC calibration still needs to be done, and there's a few other minor bugs I need to fix before I finish it off. But this is going to be the new board. This is the new schematic, similar to the old one, but well, this is page 1. Let me show you page 2. This is page 2. And as you can see, I'm going to zoom in on one of these op-amp circuits, and you can see here's my my FET, my resistor, my current sense resistor, and then my feedback circuit that goes to my analog to digital converter. Anyways, that's the circuit. Let me show you the actual unit. Well, here it is. I'm missing a knob. I still need to get one. I bought some of these binding posts for speakers, I think, but I don't know. They seem to work pretty well. You can see here I kind of made a mistake with the Dremel when I was cutting the hole. But other than that, there it is. Let me see if I can adjust the sliding and give you some better picture. There it is. This used to be an old SATA drive, or RAID drive, should I say. That's a little dirty. And I took it apart, cut a big hole and mounted a fan. Reused the same power supply that's in there. Can you see a little ferrite bead there? Or yeah, the ferrite coil, loop, whatever it is. Put another fan. There's my board. There's the third rendition. Put a fourth fan in here. Doesn't have a power switch, unfortunately. I'm gonna have to add one somewhere, and I'm thinking I'm gonna reuse these old switches to manually turn on the fan whenever I want to, or do the power control. But anyways, let me give you a better look. This is looking at it from the top. Probably can't see very much, but there's a whole mess of wires in there. Got this heatsink in at Amazon. It was like $16, and I had to go get some L brackets just so I can mount it on. Luckily, it fit right between the posts, top and bottom. So I was kind of able to use that as a reference point as to where I was going to mount this, or how high. And even though this sticks out a little bit, it doesn't stick out past the cover, so that's just great. And can't see too well, but they're in there. Anyways, let me show you the board. That has this little screw up here, where the cover just kind of comes open here. Let me take the screw off before I do anything. Anyways, there's my pot, there's my LCD. I only use a 4-bit, not all 8 bits, and for the LCD. I had to add this big honking capacitor here to filter out some of the noise from the fan, or the fan should I say, because I'm running 3 of them. Each fan runs at 400 milliamps. It's an 80 millimeter fan, so it puts out. It's small in it, but it puts out quite a lot of air, and they're pretty loud too. So there you go. So here's my keypad connector, my LCD connector, which on the new board I flipped for the wires to go up instead. I moved my USB port. I moved it over here, and I moved my programming port, which at the time I didn't really know how I was going to fit all this in here together. I put it up here on this side so I can have easy access from the side. But anyways, let me show you the new board. Well, let me show you the old board. Actually, let me show you all the old boards. So this is the first rendition of that board when I first started this project. As you can see, it's got some stuff done to it, but I had to make a few changes. I had to do a lot of testing and modding. Anyways, here's the back side. Yeah, it didn't work out too well. So then I moved on to version 2. Actually, that was version 0. Let me move this out of the way. This is version 1. I made it a little bit smaller. And I populated a lot of stuff, and I got it to work pretty well, but I needed more better circuitry, I guess is what I'm wanting to say. I had the heat sinks mounted up here in the back. I had 2 for this one, but it was a different heat sink at the time, and then I just moved it all to 1, and yeah, it still didn't work too well. As you can see, I blew these caps here because I accidentally touched 24 volts coming out of that power supply to the 5-volt line, or the 12-volt line should I say, and it just blew everything right to hell, which is alright. So then we moved on to the third rendition of this board, which is the one that you see here, and here's this one. This one works pretty well. There's still a few issues I had to solve. And here's the back. I don't know if you can see too well. Come on, focus. But there it is. There it goes. And there it went. So now we move on to my 4th rendition of this board. Let me grab that one. Still the same size as you can see, but I moved my USB connector. Yeah, my USB connector over here. I moved my programming port over here where it says ICSP1, and I moved everything. Took out the heatsink. Uh-oh, need to focus here. Took out the heatsink and changed the power connectors. Added a second op-amp control for a second FET, and just kind of scooted everything over, and then added some connectors to the back. Since it's going to go in this unit, it might as well have connectors in the back for the cables and the temperature sensors. Anyways, this is the board, and so there you go. Took quite a while to get this to work properly, but I got it to work. So I moved, as you can see up here, I still have the wires that go to the FET in the back. These are my temperature sensors that I moved to the back on the new board. Here's my fan control, which if I remember right, I think I moved that to the back too. Yes, as a matter of fact, I did for 3 fans. Yeah, fan 1, fan 2, fan 3. So instead of using one large FET, I use 3 smaller individual FETs that can handle about 5 amps continuously, according to the data sheet. But who knows? One never knows. So, anyways, let me go over the components I've chosen for that. Now, for this FET, for my actual FET, I didn't have that set up for you on Mauser's website, because that's where I usually get all my stuff. Let's see what we have here. Let's go to the data sheet for that, shall we? So this is a linear MOSFET, and it's rated at 100 volts, 110 amps capability with less than or equal to 18 milliohm RDS on. Now the reason I picked this FET is because of its safe operating area, which, let me find it and see if I can pull it up here. It's in one of these. Here we go. At the safe operating area right here. Well, if I can zoom in here a little bit. So I can run it anywhere in this region, anywhere up in here, as long as I meet the requirements. So I'm doing no more than 10 amps, which is right here. So this is at 10 volts, 10 amps, 10 amps, 20 volts, 10 amps, 30 volts, and things like that. But I'm working in this area, so I'm okay. I'll be all right. Anyways, let me show you the op amp I'm using. It's the Analog Devices ADA 4665-2, and it's a pretty good amplifier. I chose different other ones as well, but it didn't work well with the other ones. Finally rested on this one. This one has an offset voltage of maximum of 6 millivolts, which is still pretty high, but it's close enough to what I needed, so better than the 358, LM358 that is. Anyways, moving on to my capacitors, I use these Nippon Chemicon low ESR. So these are pretty good, rated for 105 degrees. For the surface mounts, for the electrolytics through holes, I use a low impedance Panasonic. So these are rated for 70% less on the FC series, also at 105 degrees. And then for the fan controlling transistors, it is these by International Rectifier with a 29 milliohms at 4.5 volts. So that's perfect for what I'm looking at, because I'm going to drive them with a 5 volt logic voltage. And then for the processor, I'm using the almighty PIC 18F4423. This is a data sheet for the 4420 because it utilizes a 10-bit analog to digital converter. But if we go back to Mauser and we actually type in the PIC 18F4423, it is the same version, but it's the same chip, except that it has a 12-bit analog to digital converter. So if you ever look up this particular data sheet, the only thing you're going to get on it is the analog to digital converter section, which is different than the other one. So we'll go over here to the 12-bit analog to digital converter, and it'll talk about it. And once you get past all this stuff, it goes into the special features, and then it goes into the electrical characteristics, and that's all it has on this particular data sheet for my device. But everything else about it pertains to the 4420. So anyways, let me take it apart a little bit so you guys can see how I managed to put all this spaghetti mess in there. And it's gonna take me a while, so give me a few minutes and I will be right back with the unit dismantled, and then we'll power it on. Okay, I'm back with the unit dismantled, and as you can see, here are my power wires. Here's my mounting bracket for the circuit board, which is kind of only mounted on the top. Here's the fan. Here's the two large FETs I'm using, and right on top of that, super glued actually, are the two temperature sensors that I'm using to sense the temperature of the FETs. how to make this little homemade board here so that I can have a way of mounting it, of actually connecting the wires, which I'm using 16 gauge stranded wire, and my two current sense resistors, one here and one here. So these are each 1 ohm, so this one pertains to this FET and this one to this FET. And I think for my next version I'm gonna get 2 more 1 ohm resistors, and I'm going to parallel them and maybe move these a little bit closer to each other, or maybe move these further away so that I can have 2 FETs here in parallel, bringing me down to 0.5 ohms and 2 over here. The reason for that is because if I show you over here, let me go back to the schematic. Right now I run one FET with a 1 op amp, and see if I can zoom in here a little better. And so I figure, you know, these are pretty high dollar FETs, so I think they can handle more current. So I'm gonna go ahead and parallel 1 more of these with this one, and that's for one FET driver, and then here's the other FET driver, so I'm gonna do the same for that. My actual checking what voltage I'm getting in is through a voltage divider coming in from the power supply that I connect up here, and just running it straight to my analog to digital converter. And then here, of course, is going to be the new connectors for my 2 temperature sensors, which are the MCP9700A. So they're okay. I mean, they're good for my purposes. They're not anything special. And here's where I put my 10K turn, my 10 turn 10K pot. So there you go. And everything is fed into the analog to digital converters of the PIC. So back to the unit. There it is. You can see how my setup is. So I've tested this power supply with it, and it's gone all the way up to 30 volts, and it's full current at 6 amps. But I was looking to see if it can handle even higher current, so I went and dug this thing, this monstrosity. I dug it out of my storage unit, and this is a 12 volt power supply rated at 10 amps, and then we have another one here, the switching one, rated at 13.5 at 11.2 amps, and then these two are also 12 volts at 10 amps. I'm thinking of maybe I can put them in series and double up to 24 volts and run the whole thing at 10 amps and see how my my little unit here handles it. Anyways, let me put this thing back together, and I will show it to you guys and show you how it works and see how well it stacks up to the meters. And then I'll show you with the scope here what kind of issues I'm running into and why this new revision is going to be different than the old one. Okay, let me put this thing back together and I'll be right back. Okay, I'm back. So the unit's put back together. I'm going to go ahead and put the cover on it, and that way you guys can see how this thing kind of goes together. Sorry, kind of hard to do this with one hand on what I'm doing and the other hand on something else. There we go. Almost there. This side's there, and then we just push it in, and that looks to be pretty good there. Alright, so let's bring it over here, shall we? So let me plug this in. Where is it at? Here it is. It goes over to this end. And let me see, where is it at? There we are. Got my power strip there to make sure the power's off. And I'm gonna power it on for you guys so you guys can see what it does. Yep, doesn't want to work. What's going on here? Looks like my no, there it is. Oh, there's the problem. It wasn't plugged in all the way. Sorry about that. Anyways, here you go. Powering on. You heard that? Those were the fans. So as you can see, I'm displaying both temperatures. I have my input voltage reading. Oh, focus. My focus needs more focus. I display the volts, the amperage, and the power. So by turning my little knob here, that's 0. If I turn it up to all the way that I want to, that'll take me all the way to 999. So that should be 9 amps, almost 10 amps. And that's running with a 12-bit DAC. So I gotta turn this all the way down. I wish it would stay in focus. If I press A, I go into keypad mode. Then I can just type whatever I want. What was that? Press D, it enters a value. And since I have nothing connected, well, it's not going to display anything. So let's just clear that. Then I press B for back. If I can get this to focus. There we go. Now let's get this monster going. Should be plugged in. My power leads are right here. So they're kind of short. So what I do is I connect it one input to my 10 amp and then the output of my meter to my positive input. So you can see I have them color coded, and then I have my negative input to that. Now let's turn this on. Put this here for voltage. Current, voltage. See if I can get these connectors to go on there. Again, I do apologize for this. Kind of hard to do things with one hand all the time. See if I don't cause a short over here. Sometimes I can get it to work this way, sometimes, eh. See if that works, shall we? So, turn this bad boy on, and you can see that it measures 13.8 volts, 0.7, 0.8, 0.11, and my meter shows 13.9. So I still need to figure out how to make that more stable. Let me turn this on for a second. Now you got to do it kind of with two hands. There's my current reading. It always displays 0.09, but it might actually be there, and I'm just not picking it up due to the op amps I'm using. But let's crank it up here. Let's go down to 1 watt. Sorry, 1 amp. So at 1 amp, I'm display 0.99, measuring 12 watts in power dissipation, and my meter says that it's at 0.99 as well. and my voltage, as you can see, is 12.9, and this one here 12.95. So there's you know, it's not completely accurate, but it's close enough. I still need to work on that. I want to calibrate it to where it displays right on. So we go to 4 amps. If I can get it to go down. And my display says 3.99. Oh, there goes the fan. Comes on at 31 degrees centigrade. Oh, come on. I'm dissipating 49 watts. My meter says I'm burning 3.97 volts. My voltage is dropped down to 12.6, but my measure drops down to 12.4. Now, for whatever reason, every time my fan kicks up, it always drops that voltage by 10 or 0.1 volts. So that, I still need to figure out that why, but I think it's my switching power supply, and which is why I am going to move to a new power supply with this toroid transformer is rated at 24 volts AC with 8 amp output current. So I'm gonna have to design another board the same size, and it'll be specifically for this power supply, specifically for that unit, which of course is going to mean that it's going to have to go on a different in a different case. So now let's crank it up even higher. Let's see where we're at. We're at 32 degrees. So let's crank this up all the way. All the way to the maximum number of amps that I can dissipate here. But you can see that I'm setting it to 8.92, but it's only reading 8.7. So that's because of the 1 ohm resistor, current sense resistor I'm using. So as you can tell right now, I'm actually developing 8.778 volts across that 1 ohm resistor. So that's why it's slowly shutting off my my FET. But let's see, what's the max I can reach? There, 9.78 amps, and this measures 9.81 amps, 11.99 volts, 11.77 volts at a power dissipation of 115 watts. So let's leave that running here for a minute, and we'll see how high the temperature gets. Alright, I'm not going to make you watch through this, so we'll be right back. Well, we've been running it for about a minute now, and my temperature is slowly but surely increasing to 40 degrees Celsius. Still running at full power here. I don't want to leave it too long because I don't want to burn out my resistors. They're rated at I think they were 25 watt resistors, but with the heatsink and all that, who knows. If I can get this focused, there we go. Okay, so let's turn this down. Yep, it reached 40. Let's turn this down all the way until my fan shuts off. So I'm not sure how accurate those temperatures are with the sensor sitting on the FET like that, but I would think it'd be pretty damn close. Although I'm sure that fan that's blowing right on top of it is probably not giving me accurate results. Could be running harder. Oh, there's my fan sputtering. I haven't figured out exactly why, but I think it has to do with my code, why the fan kind of sputters like that. And I think it's probably because I'm adding the temperatures when I turn it on, and I'm lowering it when I turn it off. Or vice versa, should I say. I'm lowering it to turn it on and adding it to turn it off. But anyways, that's neither here nor there. Anyways, this is the supply. I mean, this is my DC load. Well, I guess I didn't show you the keypad mode, didn't I? Let me say keypad, and then let me clear this. Let me set it to 5 amps. Oh, come on, one more time, and then we press D to enter, and it says I'm running 4.97 amps running through it. My meter says 4.96, and my fan kicked off 12.52 volts, but this says 12.36, so there's always a discrepancy there. So why don't we just do the full power? It didn't like that. So why don't we increment it only to 9 volts for now? Or 990, see what that does. There we go. 12.13, 11.84, 9.76, 9.72. So the current measurements are close, but for whatever reason that voltage doesn't seem to add up. So anyways, let's clear this and let's go back, and now we're back onto potentiometer mode. Anyways, let me take this apart here so I can show you the noise that's being generated by not just the fans, but by the switch and power supply. Let me turn on my trusty Rigel 1054Z or DS 1054. Let me plug in my phone here because it's about to die. So let me get my meter lead while that thing boots up. Oh no, it's not going to reach. But anyways, I don't need it to reach here. Let me just take this apart so I can show you some of the measurements that I see here. So we're still at 13.1 with practically 0 volts. There you go. There's my little heartbeat LED letting me know that my proc is running. And drop the screw here. And let me connect the grounds, and so you will see. So right now I am measuring the voltage of my 12 volt power supply. As you can see there, the minimum is 11.4 volts and the maximum is 12.6. So let me zoom in on this signal here. Let me set it to AC mode. Where are we? There we go, AC. And then we can go down to the 100 millivolt range. Let me reconnect this, and I'm measuring right at the tip of that cap. I don't know if you can see it there, but it's right there. And there's a noise, a nice noise that's being generated on my 12 volt power supply. So let me extend that here a little bit, speed it up, see what that does for it. And there's the high frequency noise. Oh, let me speed that up a little bit more. And there's the spike. That is what is causing problems for me. Let me slow it down a little bit. And there you go. And it's set to 100 millivolt per division, and you can see those are at least 200 millivolts per division peak to peak. So that's pretty high, and that's generating a lot of noise. And it's also being translated over to my 5-volt regulator, and as you can see, that's what it does. So if it's getting into my regulator and it's getting into my proc, which is, here's my proc voltage, still there, then you know it's getting into my analog to digital converter, and it's also getting into my that's a 12-volt line, which seems to be a little bit smaller. Well, that's probably because I have all those 4 caps over here. But if I measure the pin, there it is. There's still noise, which is about 100 millivolt noise on my op-amp circuit. That's my analog circuit. So there you go. Those are the issues that I'm running into, and because of that, I have to go back and design a power supply to eliminate all that noise. And I hear, or from what I know, toroids are the best transformers to use to make clean power supplies. Anyways, I got lucky. I got like 10 of these. I got some bigger ones, and this is one of the smaller ones, so I have 2 sizes. Well, anyways, that's it for the video, guys. I hope you enjoyed my video. If you learned anything, or you have been inspired to make one of these, I suggest go right ahead, improve on somebody else's design, or tweak it and make it your own, which is what I did. Obviously, this is my very first project like this that I've made, so I'm still learning from it. I still have a lot to learn, and hope you guys enjoyed it. Anyways, thank you for sticking around. Hope you liked it. You leave a comment, and you subscribe. I appreciate it, guys. See you next time. Bye.